So we left off the last video describing how we would need to adjust this in order to find absolute extrema, which are the absolute highest or largest value and absolute lowest value in a specified region. And what we need to do is we need to collect up a list of points that we need to check. And this collection of points we are going to get from three different places. The first thing that we need to find are critical values in the region. We also need to find critical values on the boundary. And then we're also going to check the corners of the boundary. So we're going to have, as we find all these, we're going to have a running list of points that we need to check. And the deciding factor of where our absolute extrema are is we're going to plug these points into the original function. The function tells us the actual height at that point. So how high in the z direction, how low in the z direction. Since we're only concerned with the absolute largest and absolute smallest, we just can easily pull those points out of the list by whoever has the highest z value and the lowest z value. So we've already talked about critical values in the region, and listing out the corners is going to be simple. What we're going to mostly focus on here is how we find critical values on the boundary. So we are going to find the absolute extrema of f of x equals 6 minus x squared minus 4y squared on the region, which we just call R for region, which contains all points x and y such that absolute value of x is less than or equal to 2, absolute value of y is less than or equal to 1. What this means, this region, if we just look at the xy plane and don't worry about z values right now, if the absolute value of x is less than 2, that means that x is less than 2 and greater than negative 2. You could take the absolute value of any of these points here in the center and they would come out to be less than 2. And that absolute y less than 1 means that either y is less than 1 and y is greater than negative 1. So any y value within that vertical distance there would have an absolute value that's less than or equal to 1. So we're talking about this rectangle right here. Since we have a nice neat rectangle, I'm going to start my list of points to check because we can very easily pull out those corners. And we've got corners at negative 2, 1, negative 2, negative 1, positive 2, 1, and positive 2, negative 1. So that corresponds to these 4 spots. We also are going to go through the process from earlier of finding critical values in the interior of that region. And there's nothing special you need to do to make sure you stay in the interior. We're just going to find critical values. If any of them end up outside the region, we just throw them away. If any of them end up inside the region, then we'll add them to our list. So remember, critical values are where both first derivatives are equal 0 or either first derivative is undefined. So let's remind ourselves right here as we start our derivatives what our function is. It's 6 minus x squared minus 4y squared. The partial derivative with respect to x is negative 2x, and the partial derivative with respect to y is negative 8y. And the only time that they will equal 0 simultaneously is at the point 0, 0. The only time negative 2x will equal 0 is when x equals 0. And the only time when negative 8y equals 0 is when y equals 0. So that gives us one interior critical point so far. So we will add that to the list of points we need to check. Now, since this just looks like a polynomial, and polynomials are continuous over their entire domain, we don't ever have to worry about either one of these being undefined. So again, neither will ever be undefined. So the undefined part of critical values we don't even need to do on this one, just the equal 0. So we've got one critical value in the interior. Now we need to check our boundaries, and that's why I drew these dashed lines, because those are our boundaries. We need to know when x is 2, and that's this the vertical right-hand boundary, if we have any critical points. And then when x equals negative 2, if there's any critical points. If y equals 1 or y equals negative 1, are there any critical points? So what we can do is we just go back to the original function and we replace those values and then go through the critical value process again. So one of the boundaries is x equals 2. If x equals 2, this function just becomes a function of y because we're replacing all the x's with numbers. We get 6 minus 2 squared, which is 4, and then minus 4y squared, which is 2 minus 4y squared. And critical values are when it equals 0. So it's only with respect to y. F sub x will be 0 because there are no x's here. So we just need to check where f sub y will equal 0. So the partial with respect to y is negative 8y, and that equals 0 when y is 0. So we started with an x value of 2 and found that we'll have a critical point if y equals 0. So that leads to an additional point we're going to add to our list, 2, 0. But you need to make sure that that point is actually in the region. So 2, 0 is here, and yep, it is on the boundary of our region. So we're going to add it to the list. And then we check x equals negative 2. So you can guess now at this point, it's just kind of a long process because we've got to check all 4 of our boundaries. So we go back to the original, we replace x with negative 2, we're going to get the exact same resulting f of y function. But be careful, we're not going to get the same possible critical point because now we're starting with x equals negative 2. So this is again 2 minus 4y squared, and f sub y is negative 8y, and that's only 0 when y equals 0. So we started with x equals negative 2 and got y equals 0. So there's another point to add to our list, and I might run out of space here. Now we're going to check our 2 y boundaries. We've got y equals positive 1, which is going to make this now just be a function of x. So we have 6 minus x squared minus 4 times 1 squared, which is going to be 2 minus x squared. F sub x is just negative 2x, and that's going to equal 0 when x is 0. So we've got the point 0 for x 1 for y, because we started off with y equals 1. And then for y equals -1, I suspect all this work is going to come out the same because of those squares. But we are going to get a different point to check because we're starting with a different assumption, y equals -1. We'll have 6 minus x squared minus 4 times -1 squared, which turns into +1. We subtract, again, we get 2 minus x squared. So f sub x is -2x, and that's only 0 when x equals 0. So that gives us one more point to check, 0, -1. Now, since I ran out of room in my original list, I'm going to make a new list here. And we're going to have to check all of these points in the original function. So I'm going to write that again. 6 minus x squared minus 4y squared. And the list of points we need to check are the corners, which we said are 2, -1, 2, +1, -2, -1, -2, +1. We also found one interior critical value, 0, 0. And then we found 4 critical values on the boundary, -2, 0 and +2, 0, 0, 1 and 0, -1. We need to find the functional value for every single one of these. So for every single one, I'm going to say 6 minus 2 squared minus 4 times -1 squared, and see what the functional value is. And then our ultimate decision on the max and mins are going to be the highest and the lowest functional value. So this is going to be 6 minus 4 minus 4, which is -2. If we check 2 +1, we're going to get the same thing. We get 6 minus 2 squared minus 4 times 1 squared, which is 6 minus 4 minus 4, which is -2. In fact, all of these corners are going to give us the same answer because our x and our y are squared in the original function. This is again 6 minus 4 minus 4, which is -2. So all of the corners have a functional value or a z-value of -2. Now, if we start plugging in these other critical points that we found on the interior in the boundaries, 6 minus 0 squared minus 4 times 0 squared, that's just 6 minus 0 minus 0, which is 6. And then we'll start plugging in these boundary critical values. 6 minus -2 squared minus 4 times 0 squared, that's just 6 minus 4 minus 0, which is +2. And we're going to get the same thing here for the next one. The only difference is the sign, but since we're squaring, it'll be the same. And then these last two will be slightly different. We've got 6 minus 0 squared minus 4 times -1 squared, which is 6 minus 0 minus 4. Oh, it actually gives us the same value. And then 6 minus 0 squared minus 4 times 1 squared. 6 minus 0 minus 4 is +2. So we only got 3 different values back. We got -2s, a +6, and a bunch of +2s. So the largest value in this list is going to be our absolute maximum, which occurs right here. And then the smallest value in this list will be our absolute min. And they actually occur at 4 different places, which is fine. They all give the same lowest value in all 4 spots. So we have 4 absolute minimums. So if we want to write this out in a nice test type answer, we would say we have an absolute minimum value of -2 at the points, and it was our corners. So 2, -1, 2, 1, -2, -1, and -2, +1. And then we have an absolute maximum value of 6. That was the highest value we got back. And that was only on that one interior critical point, 0, 0. So I'm going to try Wolfram Alpha one more time, see if it can give us a nice graph that shows us, or at least confirms our results. So we're going to type this function in and see what it looks like. 6 minus x squared minus 4y squared. And although it doesn't go out all the way to positive and -2 on the x-axis, you can see that we definitely have that absolute max there of 6 right in the center at 0, 0. You can even look at the contour plot. And we see, remember, these lines are connecting values of common output. So all of the values on that inner ellipse have the same output value. So it looks like maybe right in the center here, since this is nice and symmetric, we're going to have either a max or a min. We can't always tell from the contour plot whether it's a max or a min, but I can definitely tell that something's going on there at x equals 0, y equals 0. And we were able to see numerically and also from the graph that it's a maximum, which is exactly the same thing we said in our answer. Absolute maximum value of 6 at 0, 0. Now the minimums are kind of hard to see because it doesn't block us off between -2 and +2. I'm sure there's a way that I could type it in up here to show that specific area. But if you imagine cutting this thing off in a rectangle, at the 4 corners we would have absolute mins of -2.